Welcome back. So this is part two of our discussion of adaptation and chemotaxis. And in the previous vignette, what I did is just try to give you a sense of what the experimental system is and all the amazing experiments that have been done. I think sometimes you hear the slogan that this is the best understood signaling system in all of biology, and I think there is a legitimate argument for that. And even if it's not, for sure, it's one of those canonical things that I feel like anybody interested in the quantitative aspects of biology needs to know about. Let me say that, this is the result of like a 50-year program of intense and rigorous discussion and experimentation and thinking on the part of many people, for sure. But I guess I am going to single out the work of Howard Berg. But there are really many, many people that have been involved in this, doing incredibly clever, beautiful things. So the thing I'm going to do is I'm going to primarily focus on one class of experiments that was done by Victor Sorek and Howard Berg. And, I hope that you'll recall back to earlier in the course when I talked about experiments to change your life for. And the way I want you to think about this is that such experiments, when I talk about them, yes, they should definitely be thought of as an endorsement of the thing that I'm talking about. But sorry, I had to turn off my phone. But they should not be thought of as any sort of negative commentary on anything else. They're simply just a statement about, okay, here's an exciting case study, and what I want in an exciting case study is a beautiful quantitative experiment that led to measurements, something where one can see one's way to doing simple estimates, where it's clear what kind of models one might write down. Those models have implications, often in the figure one sense. The model is something that we can do sort of in the setting of either a blackboard or me sitting here like this and jotting things down without too much horrific calculation, although I admit that things like figuring out the Fano factor for the two-state transcriptional circuit was a grind, a grind worth doing, but a grind all the same. And that leaves me puzzled as always about the nature of pedagogy and the nature of learning and the nature of passion and the nature of pleasure. I guess what I would say is that there's certain people, and when they give talks or when they teach, I just like listening to them, and they could talk about more or less anything. And then there are other people who just, their style strikes me as obscure or something. And so, at any rate, I yearn to be both inspiring but also capturing the essential elements of the technical content of the thing. And so, at any rate, okay, so this is a great, I bring all that up just because, in the context of what does one talk about in a course, what does one write about in a book, what I'm looking for is specific case studies that illustrate general principles. And, this one has got that in spades. So what is the experiment? The experiment, as I already mentioned in the previous vignette, is basically we want to understand the dose response curve, so shown at the bottom. And the dose response curve that you see at the bottom is trying to indicate that there's high activity in the absence of chemoattractant, which means the motor keeps on flipping its direction. And as the amount of chemoattractant increases, then the cell will continue along its way without reorienting its motors because it detected some chemoattractant. So that leads to a reduction in activity of the signal that says switch your direction. The way that this was measured was by looking at fret pairing, and I'm not going to go into the details of the experiment, but maybe I should just at least show you what the idea was. So this is and the experiment of Sorek and Berg, and what they're looking at is the proximity of key Z and key Y P. And just as a reminder about fret, the idea is that you have YFP and CFP. The CFP, when left to its own devices, like you see here, it gives off this light. If it gets close to YFP, the light emitted from CFP inspires YFP to give off photons and thus reduces the intensity coming off of the CFP. And so that's the idea of the experiment. So maybe I won't go back to that previous slide. And what you see at the bottom down here is the fret, which is a surrogate for activity, as a function of the added methyl aspartate, which is the chemoattractant of interest. And this is a collection of different mutants, and indeed that strikes right to the heart of this question of adaptation. In other words, this series of mutants are meant to mimic the different states of adaptation, although they're hardwired in the context of this experiment. So the way I would like you to think about this is that the cell is going to move around in this space spontaneously in the presence of chemoattractants, whereas in the case of Sorek and Berg, they hardwired it. So again, what's the experiment? The experiment is measure the activity. And the way they do that is a bit indirect. What they're trying to figure out is key Z, which is the thing that takes the phosphate group off of key Y, if I remember correctly, is key Z in the proximity of key Y and doing its job? If so, that means that key Y is phosphorylated, and so that's a statement about the activity of the receptors. Okay, so we're using a downstream messenger molecule, the key Y, whether it's phosphorylated or not, to tell us about the activity of the receptors. And what's plotted on this axis is one makes a step in the chemoattractant, which is what fakes the cell out into thinking that it's actually it's going in the right direction in terms of a gradient. And then the fret signal is measured. And what we're interested in a way, is trying to work out the theory that leads to these curves. So, I should say, and I like to say often, then this would probably be irritating to him that I say so, and it's not meant in that spirit, but, I'm really very much a Ned Wingreen groupie, and there's a couple of papers by Keimer and Wingreen and company, Rob Indris, so Keimer and Indris and Wingreen, that are really cool on this stuff. And then there's also some papers that are really fantastic by Mello and Tu. Most of these were in PNAS. I guess if one is really keeping score, I think that Mello and Tu were ahead of Keimer and Wingreen and company as in terms of time of publication or whatever. But for me, I'm talking about like in my heart of hearts. I think with great admiration of Yuhai Tu and Ned Wingreen for the great work that they've done in these things. And to me, they're all people that have done great things in this arena. So what I want to do is I want to try to give you in this vignette not the part about adaptation, but just understanding how to reason out the behavior of the chemoreceptors themselves and their activity. And then once we've got that in hand, the next vignette will be about the adaptation part of the story. Okay, so here's the basic picture. So when we talk about statistical mechanics or kinetics, we need to identify our states. And in the statistical mechanics setting, what I'm going to do is I'm going to write down the states and I'm going to write down their weights. And then that will allow me to compute the probabilities of various things, such as the probability of being active. So for example, if I'm interested in the probability that the chemoreceptors are active, then what I want to do is I want to find the statistical weights of these two states and divide by the sum of all the statistical weights. That's the plan of action. Note that this is like I said in the last vignette, this is one of many, many, many examples of molecules that can exist in an inactive configuration, shown on the left, these two, and an active set of configurations shown on the right by these two. In this case, there's 4 microscopic states because the inactive guy can either have a ligand or not, and similarly, the active guy can have a ligand or not. So that's the upshot. So what we want to do, I'm going to write down what's called once again the MWC model. So this is a statistical mechanical model of allostery, and since it's been a little while since we introduced this last time, I'll just review for you. So this statistical mechanical model of allostery. I remind you that allostery it's a word that, there's, if you read out in the literature, it's got various nuances about how people define it. For my purposes, what I have in mind is an allosteric molecule has a few signatures. It can exist in an inactive and in an active conformation or set of conformations. And the binding of some effector molecule has a different binding energy or a different KD depending upon whether or not that molecule is in its inactive or its active state. So, hemoglobin is not an enzyme per se, but it actually is described well by this MWC model in the sense that when hemoglobin is bound by oxygen, in general, it's in a different conformational state than when it is unbound by oxygen. And probably you will do a homework problem along those lines. But, I can think about the nicotinic acetylcholine receptor, which is an ion channel. That thing is closed or open. Those are the two states. But the binding of the neurotransmitter, the acetylcholine, will change the relative probability of open and closed, and so on, transcription factors and whatever. So for my purposes, what I'm going to do is I'm going to describe the states, and I'm going to just straight away write the weights, and the first couple of states that I'm going to write are going to be the inactive, and then I'm going to write my two active states, where this little thing dangling off is supposed to be the phosphate group. So so these are the active states, these are inactive, and just to note that like this. And now, so I need to put my ligand. So let's make the ligand like this. So there are my 4 states of activity. And what we need to do is we need to write down the relative energy. So I'm gonna call this guy a weight e to the minus beta epsilon, and then this guy is going to have a weight e to the minus beta epsilon times the ligand concentration divided by Kd inactive. Maybe that's cumbersome. Why don't we just call this Ki? So this is the Kd for binding in the inactive state, and then this guy is going to have a statistical weight 1, and this one's got a statistical weight of L over Ka. So L is the concentration of this ligand. So L, this is the ligand, which in our case is chemoattractant. And so, that's it. So if I want P active as a function of ligand concentration, well, as always, I write that as the sum of the statistical weights. So here I have in the numerator the 2 pieces that contribute to the active state, and then I'm going to change my notation a little bit. So here's the I plus e to the minus beta epsilon. And a reminder, beta is 1 divided by kBt. So this is it. This expression is the expression for the activity of the chemotaxis receptor as a function of the ligand concentration. It depends on 3 parameters, all right? So what are the 3 parameters? Let's see, let's add another page here so that we can make a few notes. So it depends on 3 parameters, and only 3. So epsilon is defined as the energy difference between the active and inactive conformations, right? And why do I say that? Because let's prove that. Why? Set L equal to 0, and then P active for the case in which L is equal to 0 ends up just being 1 over 1 plus e to the minus beta epsilon. This is also called the leakiness. Why is it the leakiness? Because it tells you about how active or inactive, depending on which point of view you want to take, this system will be in the absence of ligand. In other words, it will not be perfectly inactive or perfectly active. And let's say that epsilon is negative, meaning that the inactive state is favored. If epsilon is negative, then in that case, this denominator, this thing right here, will be positive, and the probability of being active will go down. On the other hand, if epsilon is positive, if epsilon is positive, then this term, the larger and more positive it is, this term goes away and the probability of being active goes to 1. And so epsilon is going to control the behavior in the absence of the effector, which is the thing that tunes whether or not we have activity or inactivity. So at any rate, that's the parameter epsilon. And then I have, in addition, I have Ka, which is the Kd for binding the active configuration. And then I have Ki, which is the Kd for binding the inactive configuration. So stare at this equation. It's very subtle, and I tried to make that point last time, but let's check it out. If Ka and Ki are equal, then this thing has no concentration dependence. There will not be any dependence on L. So the very wicked and subtle assumption made by Monod, Change, and Wyman was that the binding depends upon the conformation. And that's cool because what it does is it gives the capacity for the effector molecule to shift the equilibrium from one conformation to the other. And that's in fact what happens in a lot of these cases. Okay, so what's the consequence? The consequence is this. I can plot P active as a function of ligand. So this is basically the equation that I just showed you. So I'm literally here. So let's grab it. I can grab this whole thing. And I will bring it down here. Paste it and shrink it. So what's being plotted then is P active C is what's on the, or L is what's on the y-axis, and then L is the quantity that's plotted here, the chemoattractant concentration. And so you can see, these curves, it's active in the absence of chemoattractant, and then when we add chemoattractant, the thing becomes inactive. And the reason is because the motors are going to be shut off. And what you can see here is that what I've done is I've plotted these curves where I've kept Ka and Ki fixed, and the only parameter being changed from one example to the next is the difference in energy between the inactive and the active conformations. And this is meant to give you a hint, anyway, of what kind of thing is going to lead to families of curves like this. Okay, now if you stare at these curves, you might say to me, well, hold on a second, the data is a lot more nuanced than what you're plotting here, and I agree. So, the little steps for little feet. We've done our first piece of business. Now I can try and show you a little bit more about what both Mello and Tu and then Wingreen and company did. So the first consideration was, well, these things cluster together. This is something that Dennis Bray and others have talked about, that these Grant Jensen has really beautiful electron microscopy images of this. The chemoreceptors cluster together. And so I can do my states and weights business all over again. This is a really, really fun calculation. I leave it to you as an exercise. I'm not going to do it. I'm probably not going to give it as a homework. But, what I'm doing is I'm enumerating here all the possible configurations. So here, let this go away. In this group, if there's n molecules in the cluster, then there are n distinct states of interest here because there are n ways for me to have one ligand bound. Here, there's n choose 2 ways to have the ligand bound. And so, you have to be kind of careful about it. But when all the dust settles, this ends up being nothing more than an exercise in the binomial theorem. That's the key point. Very, very interesting and fun. So, this is the next level of model. And I'm plotting up here the activity as a function of the number of receptors in the cluster and also the sensitivity down here. But even that's not enough. So then the next element in their analysis was to say these receptor clusters are actually heterogeneous, meaning that there's both TAR and TSR, or what I don't know, there's a lot of cobwebs here. I may have forgotten the names. But there's more than one species, and once again, it ends up being an exercise in binomialness, and so you end up getting this very simple and beautiful expression. And so, when all the dust settles, there's basically sort of a sophisticated MWC, Monod-Wiemann-Schonje analysis that has, a couple more parameters. And in light of that, you can characterize these different mutants that I've just been talking about here, these mutants, as collectives of heterogeneous clusters of different sizes. So, there's a lot of nuance there, but it's nuance that's interesting and kind of gives you a sense for the progressive sort of sophistication of models. Like I would never start with the full cluster, never. And it doesn't matter. Like even if I knew a priori, which actually I did, that there are clusters, I would still do the single receptor case first, because I need to practice the craft. I need to understand, what are the elements of the simplest model, and then what does clustering bring? What does heterogeneity bring? Each one of those is an interesting question, and at least for me, I'm slow, but for me, the only way I can appreciate those things is by first taking a look at the trimmed down model and seeing what it does and what it's lacking, and then putting in the next effect. So that's my introduction to the statistical mechanics of thinking about these chemoreceptors. And where we're going next now is I want to talk about how the system actually perceives a temporal change in the amount of chemoattractant and thereby shifts its midpoint by adding methyl groups and removing methyl groups from the receptors, which effectively, for our purposes, changes the delta epsilon, or the epsilon that I've used here, which is the difference in energy between the inactive and the active states. It's really a great story.